They weren't just dinosaurs. They were living skyscrapers, stretching longer than basketball courts and weighing more than a dozen elephants. These titans of the prehistoric world reshaped landscapes, crushed trees beneath their feet, and towered over anything that dared to share their space. From South America's plains to Africa's ancient riverbeds, their fossilized remains whisper of beasts too massive to imagine. But who's the true king of giants? Long before the great asteroid impact ended the reign of dinosaurs, sauropods towered over all other land animals. These four-legged herbivores had huge bodies, sweeping tails, and incredibly long necks that allowed them to reach vegetation far above the ground. They roamed ancient floodplains, forests, and river valleys, sometimes gathering near water sources to drink and feed. Their sheer size still amazes us, and many scientists consider them the most massive land creatures in Earth's history. Sauropods were not simply large reptiles. They grew to lengths of up to 30 meters or more and could weigh dozens of tons. Despite this enormous size, they had hollow spaces in their bones to reduce weight, allowing them to walk without collapsing under their mass. These air sacs were linked to a specialized breathing system, letting them move oxygen around their huge bodies. This adaptation gave them an advantage in warm, lush environments filled with ferns, conifers, and flowering plants. Their remarkable necks also made feeding more efficient. A sauropod could stand in one spot and graze across a broad area, lifting or lowering its head to reach leaves or shoots. Some might have specialized in feeding high in the canopy, while others clipped low-growing plants near the ground. This feeding style may have let multiple sauropod species share the same habitat, each targeting different layers of foliage. During the Jurassic and Cretaceous periods, sauropods became a common sight on several continents. Fossil sites in South America, Africa, and North America reveal that these creatures adapted to diverse habitats, from humid coastal plains to drier inland regions. Their global spread shows how successful they were at surviving and reproducing in many climates. Sauropods owed their remarkable size to a set of clever physical features. First, their vertebrae contained hollow chambers that reduced weight while preserving strength. This construction, called pneumaticity, meant air sacs were woven through parts of their skeleton, making the bones less dense. With lighter bodies, these dinosaurs could grow longer and taller without overloading their legs and feet. Their limbs were thick and pillar-like, built to carry vast amounts of weight. Each foot resembled an elephant's, with padded soles that absorbed stress. Though heavy, sauropods maintained a balanced stance because their tail acted as a counterweight to their long neck. When they walked, each step was careful but firm, preventing the body from tipping forward. This stable posture helped them move across varied terrain, including muddy plains and soft riverbanks. The neck itself was a marvel. Consisting of many vertebrae, it could stretch astonishing distances. Some species might have had 14 or more neck vertebrae, each packed with air pockets. Muscles attached to tall spines on the vertebrae, giving the neck flexibility and power. This design allowed them to feed on high treetops or sweep the ground without constant repositioning. Even their heads were built for long hours of grazing, with peg-like teeth ideal for stripping leaves or grinding up soft vegetation. Another secret to sauropod success was continuous growth. Many reptiles today keep growing throughout life, but sauropods took that approach to new extremes. Fossilized bones show growth rings, similar to those in trees, indicating that these dinosaurs steadily added mass year after year. Rapid growth rates in their youth likely helped them outgrow predators. By reaching huge sizes, adult sauropods reduced their chances of becoming prey, although hatchlings were still vulnerable. Circulatory and respiratory adaptations also played a role. A large body requires efficient transport of oxygen and nutrients. Air sacs provided continuous airflow through the lungs, boosting oxygen uptake. A powerful heart, possibly assisted by additional regulation in the neck, ensured blood could reach the brain when they raised their heads. All these traits combined to create the ultimate herbivorous tanks. Hollow, weight-saving bones, massive legs, elongated necks, and specialized breathing systems turned sauropods into living towers. This blueprint for giant size was so successful that it appeared in multiple groups of sauropods, driving some lineages to extremes in length and weight. Among all sauropods, a special group called Titanosauria reached the upper limits of size. Fossils from South America, Africa, and elsewhere reveal that titanosaurs grew even bigger than many earlier giants. Their name reflects the Greek Titans, mythical beings of immense power, which suits dinosaurs that could measure over 30 meters long. Argentinosaurus is a prime example. Discovered in Argentina, it is often hailed as one of the largest dinosaurs known. Although incomplete, its bones point to a creature exceeding 30 meters in length and possibly weighing more than 70 tons. Scientists have uncovered vertebrae the size of adult humans and limb bones that dwarf any current land animals. Even so, exact measurements spark debates because few skeletons are found in perfect shape. Patagotitan stands alongside Argentinosaurus in terms of fame and mass. Also from South America's Patagonia region, it is represented by more extensive remains. This has given researchers a clearer idea of its body proportions. Early estimates suggest it might rival or surpass Argentinosaurus in overall bulk, though different studies yield slightly different numbers. Dreadnoughtus is another colossal titan. Named for its sense of being fearless, Dreadnoughtus showed a robust build with a wide midsection and thick limbs. Based on its shoulder, hip, and limb bones, it might have weighed around 60 to 65 tons, though new methods often revise these figures. Even with uncertain exact numbers, it ranked among Earth's heaviest land creatures. Feudalonchosaurus, also from Patagonia, further demonstrates the variety within titanosaurs. Its name means giant chief lizard, referencing its massive form. Though not as famous as Argentinosaurus, it underscores how diverse and widespread these towering herbivores were. Other sauropod wonders include Brachiosaurus, known for its steeply angled back and tall forelimbs, and Diplodocus, with a whip-like tail. While not always in the same weight league as the biggest titanosaurs, they were still enormous and roamed different parts of the Jurassic and Cretaceous worlds. Each giant offers clues about how dinosaurs diversified. Some had longer necks, others more muscle mass, and still others specialized teeth or armor. Yet they all shared the hallmark of colossal size, shaped by environments with abundant plant life and few obstacles to scaling up. The variety of megasauropods testifies to the many ways evolution can reach extremes, producing towering animals that still spark wonder when their fossils emerge from stone. Towering sauropods needed predators that could challenge them, and giant theropods rose to the task. While not as massive as the largest herbivores, some meat-eaters approached lengths and weights that turned them into formidable hunters. These carnivores, walking on two powerful legs, boasted massive skulls and jaws lined with serrated teeth. Tyrannosaurus rex is perhaps the most famous. Found in North America's late Cretaceous formations, T. rex measured around 12 meters in length and weighed up to 9 tons. Its skull could exceed a meter in length, providing space for large muscles that granted a bone-crunching bite. Some scientists suggest T. rex might have roamed solo, relying on ambush tactics and strong senses of smell and vision. Giganotosaurus and Carcharodontosaurus were similarly big carnivores discovered in South America and Africa, respectively. Giganotosaurus approached T. rex in size, with a slightly longer body but a different skull shape. Carcharodontosaurus roamed in a region that also hosted giant herbivores, such as Paralititan. Both likely specialized in tackling large prey, though it remains unknown how often they challenged truly giant sauropods. Spinosaurus stands apart from typical theropods by its sail-like back and crocodile-like snout. Growing over 15 meters long, it may have hunted fish in rivers and lakes, yet it could also scavenge or attack land-based creatures. Spinosaurus bones suggest semi-aquatic habits, a rare trait among dinosaurs. Its robust forelimbs and elongated jaws gave it a unique advantage in watery environments. These apex predators might not have singled out the biggest adult sauropods too often, since a well-aimed tail strike could be deadly. More likely, they targeted younger individuals or used group strategies when facing colossal herbivores. Some fossil sites reveal multiple theropod individuals together, hinting at possible pack behavior. However, such claims remain debated. with many experts seeing them as temporary feeding gatherings rather than coordinated packs. Each giant theropod had specialized tools. T-Rex had a crushing bite. Giganotosaurus had quick reflexes for short pursuits. Spinosaurus adapted to watery habitats. This diversity allowed them to spread across different continents and times, always at or near the top of the food chain. Where these predators overlapped with sauropods, they formed tense ecosystems in which massive size did not always guarantee safety. Large herbivores and giant carnivores shared a delicate balance. Sauropods shaped landscapes by consuming huge amounts of foliage. In turn, top predators managed herbivore populations, preventing unchecked plant destruction. Each species carved out a spot within the Mesozoic ecosystems, sometimes overlapping in diet or territory. Sauropods could travel in loose groups, allowing them to detect threats early. Younger or weaker members stayed near the center, with larger adults forming an outer ring. Tracks and fossil sites suggest that some might have followed seasonal routes, trekking to find fresh feeding grounds. Water sources were vital for quenching thirst, and crowding at rivers or lakes brought multiple species into contact, both peaceful neighbors and hungry carnivores. When a giant theropod like Giganotosaurus approached, it might single out juveniles or weakened adults. Even a towering sauropod was not invincible if alone or cornered. A well-timed ambush could cripple a leg, but direct attacks on fully healthy adults were risky. Some wounds on sauropod bones show partial healing, implying that they sometimes survived predator encounters. Meanwhile, predators not only hunted live prey, but also scavenged, devouring carcasses that supplied massive amounts of meat. Other herbivores, such as hadrosaurs or ceratopsians, filled different roles. Though smaller, they formed herds and ate different plants. But the largest sauropods, by sheer volume, had the most dramatic effect on vegetation. Stripping bark, flattening undergrowth, and dispersing seeds through their droppings, they functioned as ecological engineers. Their presence could alter plant species composition over time. Carnivores would have followed these herbivore herds, taking advantage of any feeding congregation. Competition also played a role among predators. If multiple giant theropods inhabited an area, they might specialize in different prey. One might excel at tackling juvenile sauropods, while another targeted mid-sized ornithopods. This partitioning reduced direct conflict, but kept ecological pressure on large herbivores. The quest to understand giant dinosaurs begins with their fossils, bones, footprints, and even rare skin impressions. Paleontologists often find just a piece, like one vertebra or a single limb bone, that hints at an animal of immense size. Over many years, more pieces have been discovered, each adding to a puzzle that spans continents. Researchers work in remote deserts and high mountains, carefully removing rock layers to reveal these precious clues. Scientists have come a long way in estimating the size of these giants. Early on, researchers made rough guesses by comparing bone lengths to those of living animals. These guesses often varied widely. Today, new tools help improve these estimates. By measuring the circumference of major bones like the femur and applying mathematical formulas derived from modern animals, scientists can calculate approximate weights or lengths. When a femur from a new dinosaur is found to be 20% larger than that of a known species, experts scale up the rest of the skeleton accordingly. This method helps when only parts of the skeleton remain. Laser scans and 3D reconstructions now let researchers rebuild missing parts of the skeleton. Using computer models, they can test different muscle attachments, calculate lung volumes, and even simulate how the dinosaur might have walked. This modern approach helps refine mass estimates and offers clues about movement. In addition, thin slices of bone are studied under microscopes. By examining growth rings, scientists can tell how fast these dinosaurs grew, how old they were when they died, and get hints about their metabolism. Many large dinosaurs show rapid growth in youth, with a slower rate as they age. However, challenges still exist. Fossils are sometimes crushed or warped by earth forces, which can change measurements. Soft tissues rarely fossilize, so scientists must guess the width of the chest or belly. Even the shape of bones can vary among individuals, making it hard to say what is typical. Disagreements continue too, with some studies arguing that a particular bone belongs to one species, while others think it comes from a different one. Each new find or reanalysis shifts the size estimates. The Mesozoic world was not uniform. Throughout the Jurassic and Cretaceous, continents shifted, climates fluctuated, and sea levels rose or fell. Some regions were warm and damp, cloaked in dense forests of ferns, cycads, and conifers. Others had open plains dotted with smaller plants. Sauropods thrived in places with consistent food supplies, where monsoonal rains or river floods guaranteed fresh growth. In South America's prehistoric Patagonia, for instance, fertile floodplains gave rise to thick vegetation. Here, massive titanosaurs evolved, harnessing abundant resources for their giant bodies. Meanwhile, in North America's late Cretaceous, a shallow inland sea split the continent. Low-lying floodplains teemed with hadrosaurs, ceratopsians, and other herbivores, while big predators like T-Rex staked out prime hunting spots. Ecosystem diversity also came from geographical isolation. Gondwana, which included South America, Africa, Antarctica, Australia, and India, had unique dinosaur faunas distinct from those in Laurasia, North America, Europe, and parts of Asia. For example, giant Carcharodontosaurids and Abelisaurids hunted in the southern continents, while tyrannosaurs and ceratopsians dominated in the north. Climate shifts influenced dinosaur distributions. Warmer global temperatures supported lush plant growth near polar regions, letting some species expand. But dryness in certain mid-continental areas might have restricted giant herbivores, forcing them to migrate or adapt. Paleontologists interpret changes in dinosaur communities in the rock layers, linking these transitions to shifts in environment or sea level. Large herbivores acted like ancient bulldozers, trampling through forests and fields. By doing so, they helped certain plants spread their seeds. Some hypothesized that these dinosaurs also aided in soil turnover, mixing layers as they trudged along. Streams, wetlands, and meandering rivers formed vital corridors. If one region turned too arid, sauropods could follow waterways to greener lands. Predators, in turn, tracked these migrations or resided in key choke points. Seasonal movements might have resulted in a dynamic interplay of hunting and evasion. The puzzle pieces of footprints, tooth marks, and skeleton sites reveal a vibrant web of life. Even smaller organisms like mammals, crocodiles, and insects found niches in the spaces left by towering giants. Taken together, the Mesozoic environment bristled with competition, cooperation, and survival strategies, all set against a planet that was still shifting beneath their feet. The story of giant dinosaurs never lost its appeal. Early discoveries in the 19th century sparked worldwide curiosity, leading to exhibits in grand museums. Enormous mounted skeletons overshadowed onlookers, fueling both scientific inquiry and public wonder. Over time, more finds and improved techniques have transformed these skeletons from dusty displays into vibrant stories about life on Earth. Media attention soared with each world's largest dinosaur headline. Documentaries, films, and books spotlighted behemoths like Argentinosaurus, Patagotitan, and T-Rex. These creatures became cultural icons, starring in feature films or educational shows that reached far beyond academic circles. Children and adults alike marveled at how such massive animals could even exist. Scientists continually refine their views. Advanced scanning technology enables 3D reconstructions and muscle modeling. Paleoartists bring dinosaurs to life in vivid detail, incorporating the latest research on posture, skin textures, and potential color patterns. Even footprints uncovered in old clay flats can be scanned to estimate walking speeds or group behavior. Each discovery encourages new lines of thought about reproduction, social grouping, or parenting among these giants. Debates remain. Which species truly ranks as the heaviest or longest? Did some dinosaurs break the 100-ton mark, or are such estimates inflated? Skeptics caution that incomplete fossils force big assumptions. Still, the pursuit continues with each fresh excavation. Recently uncovered partial skeletons could shift the crown yet again. This dynamic fosters a sense of healthy rivalry among paleontologists. archaeologists, each working to piece together ancient mysteries. These giant dinosaurs also remind us how life can reach astonishing extremes. They thrived for tens of millions of years before external factors like environmental upheavals or cosmic impacts altered the planet's course. Their bones stand as evidence that Earth's ecosystems can support organisms far larger than any modern land species. Their success was no fluke. It was a testament to adaptation, growth potential, and resource abundance. We have journeyed through ancient floodplains and the land of enormous predators and gentle giants. These massive sauropods and fierce theropods once ruled a world very unlike today's. Their bones show us how life can grow to amazing sizes. Even though they disappeared in a great extinction, their marks remain on stone and in our hearts. Stone and in our hearts. Stone